Now we look at the momentum equation. In the momentum equation, we get terms like rho is constant, so we have dy, and we'll get terms that contain uv. And then when we do the time averaging, we get an average of that. So now we want to study what is then when we use Reynolds ansatz, both for u and v, what is then the average of the product? So we study now what is uv, time average. So then we insert for u the ansatz as mean plus fluctuation, for v mean plus fluctuation, and then we take the average of that. And then we compute this product, and then we get the u bar, v bar, plus the u bar, the v prime, plus the u prime, v bar, plus the u prime, v prime. So I just compute the product, and then we have to average this. Now we can average each summand. Of course, that is an integral. We can do that for a sum. And then we find out that we get, these are already averaged. So we take the average, nothing will change. That is similar to the average of the average is the average. So here it is similar for the product of that. So we get this. And here we'll get then that the u bar times that is, if we average that, it doesn't change, but the v prime, if we average that, then we get 0. So that here we get 0, because the mean of the fluctuation is 0. And similar here, we get then the mean of the fluctuation for u times the v prime, and that is also 0, for the same reason. But here we'll get a contribution. The u prime, v prime, if we take the average of that, that is not necessarily 0. And that is something that we have to model. So that means by the time averaging of nonlinear terms, we get terms of this kind. So time averaging, so thus time averaging of the nonlinear terms in the momentum equation yields then the following. It is the 6, that if we take that now as a vector, so that is now a tensor, u is now a tensor, and if we average that, then we get, similar to what we derived here, we get then the tensor with the means, but we get also then a contribution from the mean of the product of the fluctuations. And the term that we get here, that is the term that we have to model. Actually, we do it in the following way. Remember, on the Navier-Stokes equation, we have the convective terms, the nonlinear terms on the left-hand side. So we take it over to the right-hand side, and it is still multiplied by rho. So then we get something that is minus rho times the u prime average. And that we call the Reynolds stress tensor, tau r. So that is called Reynolds stress tensor. that needs to be modeled. And that means that it needs to be expressed as a function of time averages. Time average U. Because that will be, the time average will be the quantity that we work with. And then we have this new quantity appearing by the time averaging of the nonlinear terms, so then we have to relate that in some way to the means. And that leads then to the Reynolds averaged momentum equation. That becomes then the following. Now we write everything. Again, we assume that rho is constant. So then we have the time derivative of the mean velocity. So it's a vector, that's the underscore, and the bar is indicating that it's the mean. Plus, and then we have rho divergence, and then we have here the nonlinear terms, and from them we will get then these here, the mean velocity vectors will be involved, giving us the tensor. And on the right hand side we have minus the gradient of the pressure. And here we do the averaging, that just leads to that we have to consider the mean pressure. And then we have the divergence of the viscous stress tensor that we also have to time average. And this term here is then taken to this side here. That is then the Reynolds stress tensor, the minus rho u prime average. So that is then the Reynolds averaged momentum equation. And in here, the viscous stress tensor is time average. That means we have here the viscosity coefficient times the divergence of the mean velocity plus the divergence of the mean velocity transposed. So that is for incompressible flow, that is the viscous stress tensor. Okay, so we'll come back to this later, and this is the main task of turbulence modeling. To relate this Reynolds stress tensor to the mean flow. But first we look at the Reynolds averaged energy equation, and there we get something similar. So the Reynolds averaged energy equation becomes then the following. That is equation 9 in our numbering. So rho is constant, specific heat at constant pressure is constant, and then we have the mean temperature, time derivative of that. Then we have the convective term, which is the divergence of the mean velocity times the mean temperature. And you can see here, from this we will also get a nonlinear term, a term that will contain the u prime and the t prime. Of course, we can have the same argument as we had for uu for ut. That will appear on the right hand side, and then we get the following. That is then first we have the heat conduction, which is described in this differential form, the divergence of the thermal conductivity K times the gradient of the mean temperature T. So, and now we get this term that I just mentioned that is coming then from the nonlinear term here when we do the insert the Reynolds ansatz and do the time averaging. And that term is then minus rho Cp, and then as mentioned it's U prime T prime average. So that has also to be modeled. And then we have the contribution, the rate of work done by the viscous forces. And there we have some average, that is the viscous stress tensor average, that is the one we have here. We have the inner product, the dot product with the nabla operator, and then the inner product with the velocity, and that is the mean velocity. And similar, we'll get also here contributions from the fluctuations. So that is then the tau prime, nabla, and then dot u prime, and then we have to take the average of this. So that these terms have to be modeled. So then, so these and these have to be modeled. Usually it's most important to model that one. We do not focus on that. We focus now on modeling this here, the Reynolds stress tensor and the momentum equation. And we shall see at a couple of models, and we shall treat them in decreasing order of complexity. That means we take the most complex first, and then we get the less complex in the end. So turbulence models for the Reynolds stress tensor. In decreasing order of complexity. That is now the following. So the most complex one for this class of Reynolds average Navier-Stokes models is the Reynolds stress model. So there are different Reynolds stress models. So the abbreviation is RSM. And the people who have been leading in this research, that is Julius Rotter from Göttingen, also a book, and then the people who made it really practical were the people from Manchester, London, Rees, and Rodi. Rodi has later been in Karlsruhe, so 1975. I just want to give you the idea. I don't want to give you all the details that would take us too far. It's just to give you an idea of the complexity. So what the idea here is of these models, the Reynolds stress models, is the following. We multiply, so multiplying the jth component of the momentum equation and we write that in this form, nj equal to 0. So we bring everything on the left-hand side so that it looks like that. We multiply that by the, and that is the original equation. So that is, we multiply that by the ui prime. That is the ith component. That first would be u, second v, third would be w by the fluctuation. And we multiply the ith component of the momentum equation that is then ni equal to 0 by uj prime. No, not r, just uj prime, nothing more. Nothing more. And then we compute, multiplying that, we compute the average of all. That is, we compute then the following, that we have the ui prime times the nj, where we have also inserted then the Reynolds ansatz for the velocity vector and the pressure. And here we have the uj prime n, that is j n I, and then we take the average of that. That is then equal to 0. So that is the idea how we do it. And then we get by that transport equations. So, and get transport equation of the following kind.
Question.
Yes.
By n, do you mean the entire momentum equation?
The ith component of the momentum equation.
Yeah.
If I is one x momentum, y or z component. The complete momentum equation. Yes.
Yeah.
Everything is then written on the left-hand side. So the momentum equation, the transport equations we get then 11 will be then of the following kind. If we take the rho inside under the derivative, we get minus rho u I prime uj prime mean dt. If you remember, this is the ij component of the Reynolds stress tensor. So we get a transport equation for each component of the Reynolds stress tensor. Then we get here the divergence of minus rho u, and we get u I prime uj prime mean. On the right hand side we get the divergence of the viscosity times gradient of this component minus u I prime uj prime mean, and terms containing terms of the kind rho u I prime uj prime uk prime average, and so on. So it gets complicated. The good thing is that we have here a transport equation, and we know how to treat transport equations now. But the problem is these terms here. They have to be modeled. So, so those terms, that is these terms here, those terms, they have to be modeled, and they are modeled using an additional transport equation for the dissipation rate. That is the one that we saw in the definition of the Kolmogorov microscale of turbulent energy. And that is the following. Now is the definition finally here of epsilon that we have seen before. That is nu, the kinematic viscosity, times the sum over all components ij, where we have the derivative du I prime dxj times duj prime dxi. Let's see, no, that was wrong. Let's see. That is just the product. It is the dui dxj, and here it's dui dxj. So it's the product of itself, and we take the average of that. So that is the dissipation rate of turbulent energy. Let's see. And nu, that is what we already had, that is the kinematic viscosity, nu over rho. Kinematic viscosity, that is the same as before. So, since the transport equations for the components of the Reynolds stress tensor, minus rho ui prime uj prime average, they are closed, that is modeled, by for obtaining, let's see, they are modeled for the closure terms in the momentum equation, in the Reynolds average momentum equations. And so we have, and to do this modeling for getting these, we have to do another modeling, a second modeling of these higher order terms. And modeling that is called closure, so therefore this answer is also called second order closure models. So once more, to get the Reynolds stress tensor that we need in the Reynolds average Navier-Stokes momentum equations, we solve these transport equations, but in that we have to model these additional terms. So we have then to this second closure. So therefore we call these models also second order closure models. Okay, now when we have related then these terms here to the Reynolds stresses or to the mean of the velocity, then we can solve them, and then we have to think about which components do we need to solve. And then we look at this, and then we find out we can exploit symmetry there. So as the Reynolds stress tensor R tau, that is what we have there, is symmetric, the consist of 6 transport equations. And that is the following. It is, why are they symmetric? Because when we have here 1, 2, for example, that is the same as 2, 1. The product here doesn't matter. So if we have 1, 2 or 2, 1, doesn't matter. We can that is the same. And then we get finally these transport equations. We get them for the components in the diagonal. That is minus rho u prime minus rho v prime minus rho w prime. And then we get it for the off diagonals. It is minus rho u prime v prime minus rho u prime w prime, and finally minus rho v prime w prime. So those are the 6. Now I wrote the components in the usual form. So these has to be solved, these 6 transport equations, to get the 6 components of the Reynolds stress tensor. And in addition to the closure, and that is appearing then when we do the closure, we need to solve the transport equation for epsilon. And that is one transport equation for the dissipation rate of turbulent energy for epsilon. Okay, so altogether 7 PDEs. So in addition to the momentum equation, which is then 3 transport equations for the x, y, and z momentum equations, we have to solve 7 additional transport equations. So the advantage of this approach, the Reynolds stress model, is that it is the most general one. It is the most general and potentially best. Turbulence model for the Reynolds average anti-Stokes equations. But when we apply it to real problems, it's not often the best. The first disadvantage is that it is costly. The Reynolds stress models are costly because to solve them we have to solve 7 partial differential equations, as illustrated here. But not always successful. Not always successful. And examples where they fail. For example, axisymmetric jets. And unconfined, that is not in a pipeline or with a boundary, but in a free space, unconfined recirculating flow. So, that is And I should say that what I can see, they are not that much used for aerodynamics, at least, and for other turbulent flow applications, they are not that much used. There is a simplified model for RSM, for Reynolds stress models. So they can be made algebraic stress models. And then the acronym is ASM. And the trick there is by relating convection and diffusion. Convection and diffusion of the Reynolds stresses with minus ui prime uj prime, relating that to convection and diffusion of the turbulent kinetic energy. Turbulent kinetic energy. And that is just one PDE that we have to solve for that. Usually you solve it in combination with the transport equation for the epsilon, the dissipation rate that we discussed earlier, but then you have only 2 equations opposed to 7. So that is, and then you have just algebraic relations. So instead of solving the PDEs are costly. You see that now in exercise 11, when we have to solve for the x momentum, y momentum, pressure correction, and the energy equation. And here you would have 7. So, but instead you can get it down to 2. And then you have simple algebraic relations for getting the Reynolds stresses. The most common way to do turbulence modeling is using 2 equation models for practical applications. So that is then, after the Reynolds stress models, we look then at 2 equation models. And these models, and also the models that we shall discuss later, 1 equation models and algebraic models, they rely on an important approximation. So these models that we are discussing now, these models and these models, like other 1 equation models that we shall discuss later, just mention that briefly, and algebraic turbulence models rely on this important approximation, and that is the Bussinesq approximation. The Bussinesq approximation. From 1877, and it means the following. It means that the components of the Reynolds stress tensor tau ij, which are, as we have seen before, minus rho ui prime uj prime, so fluctuation in the I direction times the fluctuation in the j direction, and taking the time average of that we can express that as eddy viscosity or turbulent viscosity mu t times the expression that we have for Newtonian flow, that is the rate of strain tensor ui for the average, ui bar, so that's the mean of the ith component of the velocity vector. We take the j derivative and we add to that the xi derivative of uj bar, so the mean of the jth component of the velocity. And then we have also, to get that right, 2/3 times rho times the turbulent kinetic energy times the Kronecker delta. So what this means is that we express the Reynolds stress tensor in a similar way as we express a Newtonian fluid. In a Newtonian fluid, we don't have this, but we have then here the viscosity. And these are not the means, but just the velocity components. That means we express now the Reynolds stress tensor as we do the viscous stress tensor for laminar flow. That is the trick here. And let me just give you the abbreviations here. In here, the delta ij is the Kronecker delta. That is 1 if I is equal to j, and it is 0 if I is different from j. So that means we get only something for the diagonal terms here, for the II terms. Otherwise, this term related to the minus 2/3 rho k is 0. So that is the Kronecker delta. And in the expression for the Boussinesq approximation, mu t, that is the eddy viscosity, or the turbulent viscosity. And the k that we have already seen in the beginning, that is the turbulent kinetic energy. So in that case it is 1/2 of u prime time average plus v prime product average plus w prime average. So we take the fluctuation square and time average. That is the turbulent kinetic energy. And if we want to be precise, we should say that it is per unit mass. Turbulent kinetic energy. So, and what we shall then see tomorrow is some examples of that, and it turns out that we can do then this approximation using Boussinesq approximation just doing two transport equations. As mentioned before, for the ASM, algebraic stress model, just the transport equation for K, turbulent kinetic energy, and turbulent and for dissipation rate epsilon. But there are other options that I shall mention. Okay, so then we have seen some basics of turbulence modeling, and we are now at the stage where we really have the models that are used in Brexit, two equation models.